Good afternoon, IME 145 students. We're now in week 9, and it's time to go ahead and do a final exam review for this week's in-lab lecture or presentation. So the final exam is going to be taken in class during week number 10. We do not take the final exam during final exam week in this class. We take it during week number 10 on the last day of lab for the first 60 minutes of lab. So it's a timed exam on Canvas. You're going to go ahead and log on to Zoom and Canvas during your lab time and take the exam for that first 60 minutes of lab. Now, if you have DRC permissions to go ahead and get test time added to your test, please contact your lab instructor at least 3 days before the final exam is given, and we can go ahead and add that time on Canvas for you for your DRC time extensions. Now, you have to have your Zoom logged in with the webcam in order to take this exam. So the exam will consist of pretty much 50 multiple choice calculation questions and fill in the blanks. And I've got it actually right here. We're going to talk about it. It's basically the same exact hard copy of the exam you would take if you were here in person. We just went ahead and put it on Canvas for you. What I would recommend is studying the manufacturing process terms and the homework concepts that we've gone over the past 8 weeks in IME 145's lab presentations here. So what I've done is I've kind of gone through and I've written bullet points for different test questions. And the way it's going to work is I'm going to kind of review the class, how we went through the class. I have the test here in front of me. I'm going to make sure that you understand exactly what questions I'm going to ask and kind of what we've learned throughout this entire course. But if you remember, on week 1, we really came in here and we started learning about manufacturing as a whole, right? So we had the primary, the secondary, and the tertiary manufacturing industries we learned about. If you remember, the primary ones were like the mining industries that basically take the natural resources and create raw materials for the secondary industries to go ahead and produce consumer goods with. And then it was the tertiary industries, that's the service sector of the economy that relies on the primary and the secondary industries to produce goods in order to make money and add value to materials and keep the economy going. So I would know the difference between the primary and the secondary and the tertiary manufacturing or industries out there. From there, we learned that whenever we're going to manufacture something in either the secondary or the tertiary or the primary industries there, we usually create what we call an engineering drawing. And that engineering drawing has all of the tolerances that are needed for that part to function as intended by the designer or the engineer, the mechanical engineer. So the tolerances on that drawing that are placed on there are going to definitely affect the product's cost, right? Because the tighter the tolerance, the more expensive the part's going to be to manufacture overall. So we have to spend more time in order to get the part to that size or that within tolerance, if it's a really tight tolerance there. So that definitely covers two other questions right there. Now, when we were learning about engineering drawings, we learned that there was conventional dimensions and then there was something called geometric dimensioning and tolerancing. We first learned about those conventional dimensions in like that measuring exercise, which were literally just linear distances or angles or notes, right? So we went ahead, those conventional dimensions are basically linear distances, angles, or notes on our drawing. Well, we learned then that throughout the quarter that these conventional dimensions can lead to what we call extreme form variation, where the part go ahead and it basically can, if the part's feature starts with the maximum material condition on one side of it and then goes to the least material condition on the other, we have something called extreme form variation because our feature is basically within the limits or within the tolerance, but it changes its form based off that conventional tolerance. So we learned about GD and T and that feature control frames are how we specify GD and T callouts on a drawing out there. So I would know about those feature control frames, and that's how we specify GD and T on a drawing. I would also know about GD and T in terms of the different categories of tolerances. So I would know about the 5 different categories of GD&T tolerances. If you remember, that was the form, the profile, the location, the orientation, and the runout. Well, within those 5 categories of GD&T tolerances, we have specific callouts. Now, remember, there was basically 12 or 14 in the old days, but 12 different basically geometric characteristic symbols that you can go ahead and control your parts relationships to other features or datums with there. And that's what GD&T is all about, is preventing extreme form variation and being able to communicate your design intent on that engineering drawing. So we actually inspected using indicators that parallelism call out on the mill project number 1, and then we checked circularity, which is a form call out on the lathe project number 1 as well. So we learned a little bit about how conventional dimensions were different than GD&T throughout the quarter here. So I guarantee there's a question involved right in there. Now, once we learned a little bit about engineering drawings that first week, we came back and we talked about precision and, or we didn't come back during that same week. We talked about precision and repeatability and accuracy. So precision / repeatability, kind of in the same category there. Then we have accuracy. I'd be able to distinguish the difference on the test between accuracy and precision. I know the difference between accuracy and precision. That's definitely 1 or 2 questions right here. Now, when we were measuring parts, we wanted to be both accurate and precise at the same time. If you remember, to do that, we had that rule of 10, where we wanted our measuring device precision to be 10 times more accurate than our tolerance. So looking down here at this measuring device precision, we always want that to be 10 times more accurate. Remember, we were going ahead and taking care of that throughout this quarter when we had a lot of our tolerances were plus or minus 5 thou, which is a 10 thou tolerance, and the precision of our dial calipers, or the resolution of our dial caliper that we use for measuring, was 1,000th of an inch, 0.001. So that's 2 questions. Now, when we were reading the vernier calipers and the micrometers, we read everything to the 1,000th of an inch right there, right? So 0.001. Even though the micrometer was the most accurate handheld measuring device we've used in the lab, and it could read to the 10,000th of an inch, 4 decimal places, we read everything to a 0.001 resolution, or a 1 thou resolution right there. So I would probably be able to read a micrometer and a vernier caliper on the test, maybe a dial caliper as well, for some questions there, because we learned how to do that during the first week there. Now, later on in the quarter, we used some other types of measuring devices to check heights off of datum surfaces. That would be a height gauge, if you remember that one from the lathe project 1 and also from the screwdriver project. We use that height gauge along with a surface plate to act as a datum surface to mark heights off of right there. So the height gauge and the surface plate are used in conjunction, or used together to go ahead and get a measurement from a datum surface right there. There's another question or 2. So moving on, when we create engineering drawings, or when you create engineering drawings as a mechanical engineer, you start to put tolerances on those drawings, right? And those tolerances are what we learned how to measure week 1. And those tolerances are really going to affect the manufacturing process that we select. The tighter the tolerance, the more precise our manufacturing process must be. So if we've got tight tolerances on that part, we might not be able to get it done with traditional machining processes. So if we've got tolerances down to the 10,000th of an inch, 4 decimal places, the traditional machining processes can get it done sometimes, but not all of the time. When we go to IME 146 next quarter, you're going to learn about abrasive machining processes and non-traditional machining processes. They're more expensive than the traditional ones, the non-traditional are and the abrasive, but they get things done at tighter tolerances, or they can give you a tighter tolerance when machining using those abrasive or the non-traditional processes out there. but the traditional machining processes are what we focused on starting in really week 2 in this class, right? So those traditional machining processes, if you remember, I know all 5 are broaching, milling, turning, drilling, and sawing. So I would definitely know the definitions for all 5 traditional machining processes. I might give you a definition and you fill in the blank, or you go ahead and you tell me which process that actually was, which traditional machining process. Now, no matter what type of machining process we're working with, we've learned that all machining processes are done on something called machine tools. So machining is performed on machine tools. And when we're creating these machining processes, we're producing chips with shear stress. So we use some sort of cutting tool that has geometry in the cutting tool that puts shear stress into the part and basically removes material in the form of a chip. So we shear a chip off the workpiece. So I would know about machine tools, what they are, and that all machining processes produce chips. And I would know the traditional processes. So when we got into machining, we started looking at the different variables that went ahead and were associated with machining. We learned that every machining process has some sort of surface speed. Now, I would know what surface speed is because that's the linear velocity between the tool and the workpiece as they're passing each other. And that's in feet per minute, that surface speed. Remember, the surface speed affects temperature a lot in the machining system. And so the faster the surface speed, the more heat we generate. So ductile or softer materials run a faster surface speed than really hard materials. So the harder the material is, the slower surface speed we have to run right there. And we use these surface speeds to calculate the RPMs for our mill and our lathe or our drill or whatever's spinning in manufacturing. We're going to use that surface speed to calculate the spindle RPM for it. So I would be ready to go ahead and do an RPM calculation either on a mill or a lathe or both. I'll give you the surface speed, I'll give you the equation, the 4V over D, and I'll give you every variable you need in order to calculate the RPM for either a mill or a lathe right there. Now, after we calculate RPMs, that's going to be how fast the workpiece is spinning in the lathe and how fast the tool is spinning in the mill, right? Well, now that the tool or the work is spinning, we have to go ahead and use our cutting tool to shear chips off that workpiece. So we learned about something called a chip load. Chip load has a different set of units, whether it's a mill or a lathe. But no matter what, I would know what chip load is. It's the size of the chip we're shearing off with one single tooth of a cutter. So in the case of a mill, like you see up here in the upper right-hand corner, the mill has multiple teeth right there. So we have to give it a chip load in an inch per tooth value and end up doing a mill feed rate calculation for that, a table feed rate calculation, where we take the RPM, we take the chip load and the number of teeth that the part has, or that the cutter has, and we go ahead and we multiply all those together and we get the inches per minute that the table is supposed to move on that CNC mill. Well, chip loads for lathes are a little bit different. A chip load for lathe, because it's a single point cutting tool and it's not rotating, the part's rotating, only needs to advance a certain amount forward per every 1 revolution. So chip loads for lathes are an inch per revolution value, and there's no calculation needed. I might ask you to calculate it on the final, but you put the chip load down in for that feed rate calculation there, just like we did on our homework assignments. So be able to do not only an RPM calculation, be able to do a feed rate calculation for both a mill and a lathe. Now these chip loads and these surface speeds are really based off of the workpiece that we're cutting and the tool material as well. So we learned that there's 3 major types of tool materials out there, right? I would know what those 3 major types of tool materials are, and I would know which one runs a faster surface speed. So I would know about high-speed steel, carbide, and maybe high carbon steel, and know which one has the fastest surface speed value in relation there. So at this point, once we're ready to go ahead, we got our feeds and speeds calculated for machining, we're ready to go ahead and start cutting our parts. And really, the first machining operation that happens most of the time is sawing. So I would know the definition of sawing, how it has a multi-tooth blade, that saws have blades that go ahead and shear material off that workpiece. So know a little bit about sawing. I would know that we use cold saws and we use horizontal band saws in the shop as well. So once we saw our workpiece up into a blank, we have milling processes that occur. And I would understand the process of milling. I'd be able to define what milling is, know that it's got a multi-tooth cutting tool that rotates to basically feed material past that multi-tooth cutting tool to make prismatic looking parts. So milling's a process. The milling is performed on a machine tool called a mill. So milling's performed on a mill, and that CNC mills have, the standard ones have 3 axes of linear motion right there, X, Y, and Z. And that's all based off the right-hand rule that we use for all of our engineering science classes, right? Right-hand rule. So know how the X, Y, and Z axes are oriented, maybe know which one the tool is oriented with, which axis, like the Z axis and so forth. Now, once we have those axes as standardized in that mill, standardized throughout the world, we can start spinning our part that we calculated the speed for, the tool. We can start moving it around that we calculated the feed rate for, but based off of the direction that we cut our part, moving around the part on the outside of the part clockwise and on the inside of the part counterclockwise, we would go ahead and create a milling direction of climb milling. So there's 2 directions to mill. There's climb milling and there's conventional milling. Climb milling gets you a thick to thin chip, and that's when we go clockwise around the outside of the part because the cutter's always rotating clockwise. When we go counterclockwise around the inside of a pocket. That gives me thick to thin chips and promotes tool life and uses less horsepower. So climb milling is the preferred direction of milling in a CNC machine. Now, conventional milling might be done on a manual machine if it's old and worn out and you don't have ball screws holding the part. Or if you have ceramic inserts, this is a totally different subject for cutting aerospace alloys, you might do conventional milling because ceramics don't mind basically burnishing the tool on entry. They don't mind the extra heat that would go ahead and do it. So there's climb versus conventional milling. I would know which one we use in our CNC mills when we try to use the most. Now, after that, we learned a lot about cutting tools too. So the cutting tools, they come in a couple different sizes or standards, right? We learned about face mills for facing. We learned about end mills. We learned about bowl end mills and ball end mills. And then we learned about form tools. So I know the basics about the difference between end mills and face mills and the difference between face milling and peripheral milling. So be able to tell the difference between face and peripheral milling out there. Then when we're holding our work pieces in a CNC machine, a lot of the times we make specialty fixtures, if you remember that. So fixtures hold a workpiece in a specific location in a machine tool. Well, jig was a little bit different. We used jigs in the screwdriver project to go ahead and drill the cross hole through our caps lug right there. Now the jig was a little bit different than a fixture because the jig actually guided the tool. It locates itself on the workpiece somehow and then guides the tool in the proper location to cut. So jigs guide tools where fixtures just go ahead and locate them in machine tools. I would know the difference between a jig and a fixture definitely for this exam. After that, after we learned about the basics of milling, we started learning about drilling too at the same time, or same kind of weeks right there. And we learned that drills have a really long length to diameter ratio on there. And when they're spinning, they tend to walk off true position right there. So we like to go ahead and spot drill at an angle larger than our drill bit, like 120-degree spot drill, to locate holes on parts. So we'll go ahead and we will center drill or spot drill to locate a twist drill's location on the part. It keeps it from walking off center. It puts us on true position of the hole more so than it would if we just drilled with a regular drill bit. So I would know what the purpose of center drilling or spot drilling is on a part. Also, I would know the drilling definition, the process definition. I kind of already covered that one already. And I would know the 4 ways drills are sized. If you remember, drills were sized in the rest of the world through the metric system. Then we size them through fractions, numbers, and letters here in the US. Every drill size has a decimal equivalent, but we don't size drills by their decimal equivalent. That's not how we do that. We either order a letter, a number, or a fraction, or maybe a metric drill. Now, drills, they're always going to drill slightly oversized, right? So they drill, if I get a 1/4 inch drill, and I drill with a 1/4 inch drill, it's probably going to drill like a 251, 252 hole. So if I had a tight tolerance hole, I might choose to perform reaming on the hole then. So I would drill maybe a little bit undersized, 1 or 2 sizes on the drill chart under, about 10 thou, leaving about 10 thou of extra material for the reamer to come in and take off. The reamer is a multi-fluted tool that's very rigid and only takes off a small amount of material to make an accurately shaped hole, a nice round hole, and a very accurately sized hole. So I can get down into the 10,000ths of an inch by reaming holes. So I would know what reaming is. Now, other hole processes we learned about were boring as well. What boring is an enlarging an already existing hole. So I bore out holes that are already there to make them larger with a single point cutting tool. That's what boring is all about, using a single point cutting tool to enlarge a hole. That's like word for word from this test question right here. Now, after we're talking about holes here, right? Or hole making processes. So after we spot drill or center drill, we drill, we ream, we don't necessarily have to ream the tapped hole, but we could tap as well, right? So if we had to make a threaded hole, we would use some sort of tap to manufacture a threaded hole. In fact, I would know how threads are manufactured for internal threads, like for taps, and external threads like for dies, or you could do thread milling as well for external or internal threads. So I would know some thread manufacturing methods and know how the thread call out works for these thread manufacturing methods. I might give you a thread call out. On that thread call out, you're going to tell me if it's an A or a B thread, external or internal thread, how I'm going to manufacture that thread. You also might have to tell me what the pitch is of that thread if I give you a thread call out, or the distance that it's going to travel for 1 revolution of that screw thread. So I would know how to calculate the pitch off of a thread call out. Then we have tap drill size specifications. So if I had an internal thread, a B type of thread, right? And I needed to make it, I would have to drill a hole before I use the tap to manufacture that internal thread. So I might ask you what tap drill size and give you the tap chart from the manual on the test, what tap drill size to go ahead and drill the hole in order to cut the thread with a tap. So know how to read that drill and tap chart as well for this exam, like we did on the homeworks. So knowing those thread manufacturing methods, along with the thread callouts and the tap drill size specification with the thread pitch, is an important thing to know on this assignment. Now, I would know where the major and the minor diameters are on the thread. I may or may ask you about that one, but just know the major diameter and the minor diameter. Know all the terms we learned about for a thread. And again, thread milling can make external or internal threads. Remember that too, right? We did that on the screwdriver project, both external and internal. And thread milling was one of the only types of threading that we didn't need a thread relief for if we were manufacturing it. Now, after we learned about holes and threading, we started talking about turning processes. Look at that pulley right there. That's a big pulley on that lathe. But turning processes encompass everything we can do on a lathe. Remember, turning is a turning process. Facing is a turning process. Drilling on a lathe would be a turning process because the part is turning. So turning, I would know the difference between turning and facing on a lathe, the overall definition of it. Like facing reduces the length of the part, turning reduces the diameter a certain distance back. So know the difference between turning and facing. And I would know the difference between the radial direction and the axial direction. Axial is along the axis of the part. So it's down the z-axis of the part. So it's the length of the part. Radial direction is the diameter of the part, or the radius of it technically. It's the cross direction. So the cross slide moves in the radial direction and that carriage moves in the axial direction right there. Now, when we drill on the lathe, hopefully you know that we use a tailstock to drill on the lathe. So these are all test questions I'm giving you here. So know about what tailstocks do on a lathe and how to drill. Then we learned about many different types of work holding on these lathes as well. Work holding can basically be a 3-jaw chuck if it's the most universal work holding on a lathe, or it could be a collet chuck or a specialty fixture if you really had that, or soft jaws. But I would know the most prevalent work holding for a lathe, and that's a 3-jaw chuck. So this one you're going to see around the most likely. Now, for a manual lathe. Now, broaching, we're switching gears a little bit, is the 5th machining process we're going to be talking about. We learned about broaching. It's the only traditional machining process that can produce sharp internal corners. And so we use a tool called the broach on a machine called the broach to perform broaching. Now, in order to use an internal broach on your part, you have to first have a hole in the part that you can pass the broach through. So I would know about broaching and being able to internally broach parts like that and having to have a hole right there. Now with that broaching, if you remember, we used a lot of cutting oil for the broach. So that's a cutting fluid. The purpose of cutting fluids that we learned about were to cool and lubricate the tool and the workpiece. So there's many different types of cutting fluids out there. There's oils and emulsions. I would know that the cutting oils are kind of what we used on the broach, and then we use emulsions in the CNC. In fact, I don't even ask you about that. I ask you about the purpose of cutting fluids. So I would know what cutting fluids actually do. Well, we had emulsions and oils for our different cutting fluids in the lab right there. Now, those were the major machining processes that we learned about. We then talked about what to do in design for parts after we go ahead and machine them. So I would like to know why we use surface treatments. There's some reasons for why we use surface treatments. And so there's some reasons for that. Know a little bit why we would go ahead and specify a surface treatment on our part. I would know a little bit about the knurling surface treatment that we used in the lab on the screwdriver project. What knurling is, how it works, and maybe how it's classified in the whole scheme of things in surface treatments. We also learned about powder coating surface treatment, right? So I would know about the powder coating surface treatment process and how that's different than knurling and how that's different than anodizing. I would understand the definition of anodizing surface treatment and how that works. And then also we have non-metallic coatings right there. We also had metallic surface coatings that help prevent corrosion, like galvanizing, right? That would be one example. So I would know a little bit about metallic surface coatings. And then I would know about the metallic, the non-metallic surface coatings, and the organic coatings that we talked about. So know a little bit about surface coatings. I think I mentioned the questions already there. Definitely did. So after the part is completed, after all the surface treatments are done with it and everything, we go on to maybe a first article inspection. Sometimes first article inspections are performed before you go on to the surface treatment. Like in the case of powder coating, you might inspect your machine part before you powder coat it there. It just depends. But when we have that first article inspection report, parts go through a first article inspection to make sure all the design specifications have been met during manufacturing. So the first article inspection guarantees that all of the engineer's design specifications have been met during the manufacturing stage of that part right there. So this is a common thing they do in industry all the time. They perform first article inspections as parts come off the manufacturing line. Now, within that first article inspection, we did some first article inspections where we learned about parallelism and circularity in this class, right? So we learned a little bit about GD&T. I think I mentioned this already. I would know the tolerance types and the categories for the different GD&T callouts right there. So I would know that GD&T goes into form, profile, location, orientation, and run out types of categories right there. Now, if we have to inspect complex GD&T tolerances, sometimes your dial calipers aren't going to get you there. So out in industry, you can automate your inspection using something called the coordinate measuring machine. if you remember, coordinate measuring machines inspected parts using computer models and probes, electronic probes, like you see up there in that picture. So I can offline, I can program a CMM, just like I can program my CNC machine to cut parts. I can program it to inspect a part off the computer model, put it on the actual CMM, and then have the CMM automate that first article inspection and print out a report. Now these CMMs, they basically have 3 ways to sense parts. Not all CMMs have all 3 ways. The one in Mustang 60 has all 3 in one CMM, that microview. But if you remember, they could either tactile or touch. Like you see in that picture right there, there's a probe physically touching the part, so that's tactile inspection. You could laser scan the part and basically have a surface profile of the part with a laser scan. That's another way to inspect. Or you can use a vision system and optics, vision, video, and optics, same thing. I can use a vision system and know the size of the pixels and figure out where the presence and absences of light is and inspect the part with a camera as well. So I can inspect it 3 ways: vision, laser, and tactile touch using CMMs. Now, before CMMs, they had to use dial indicators, test indicators. They still do that heavily to inspect parts. But we learned indicators don't actually give you a measurement, do they? Indicators indicate the amount of displacement that has occurred from a reference point. So I know what an indicator is, and I would know that a dial indicator is different than a test indicator. Test indicators checked perpendicularity and parallelism, right? Because they're essentially testing perpendicular to the spindle's contact point, where the dial indicator tests parallel to the spindle or in the axial direction of that spindle. So their test directions are different and they're used for different types of inspections there. So that's going to be the dial and the test indicator. But we learned, hopefully, the cheapest and easiest way to inspect parts would be some sort of fixed gauge, most likely, like a go, no-go gauge. So those go, no-go gauges have the materials conditions put in them, those fixed gauges. So the go side has the maximum material condition in it. And the no-go side has the least material condition in it. So it's a really quick way where you can just check your part, go, no-go. You don't get a quantitative number. You get a qualitative answer of pass or fail when it comes to those fixed gauges out there. Now, once you have your entire manufacturing line going, you have to do production planning in order to figure out how you're going to manufacture all the products your company makes. So if you remember, when we started talking about engineering planning, production planning was planning everything that one company makes. So we're talking the workers, the demand. We got to go ahead and look for the capacity. Our external suppliers, do they have the capacity? We have to look at basically the raw materials that we have in there, the inventory, and so forth. So it's planning everything. It's basically the nervous system of the manufacturing company, production planning or enterprise resource planning, ERP. Now, we weren't too concerned with that, but I would know what production planning is. We more so focused on routings and operation sheets. So we learned that a manufacturing routing was basically the recipe for one single part, right? And that routing could come in multiple flavors. There could be a standard routing or a parallel and a split routing. And we actually had this set up in the air motor, we had this set up in the screwdriver project, where you have a standard routing is where you got to go from this step to this step to that step in order. Some of the steps were standard. Some of the steps were parallel, where I could switch them up. In fact, I could engrave the logo on the side of the part pretty much at any time, technically, after I go ahead and get it sized. So that would be an example of a parallel one. A split one is like where you went to your Haas CNC mill number 2 or 3 to go ahead and thread mill the body. So you didn't go to both of them and do the same operation. You picked one and you had your thread milling done on either mill 2 or 3, and that was a split routing. So I'd be able to tell the difference between a parallel, standard, and split routing on the test there. Now, the routing is kind of the overall part recipe, right? Then we have operation sheets that tell me the specific instructions for one single operation. This is the instruction sheet for the technician to grab and basically set up an operation from scratch and perform a manufacturing operation. That basically makes it so it's very repeatable for that technician to go over and basically do that operation over and over. So if they haven't ran that job in 6 months, they get the op sheet back out, remind themselves, and they go fully set it up so it can basically run as intended. Now that's really that's the end of the topics pretty much for our final exam review. Hopefully you know why it's so important for design for manufacturability skill sets to be instilled in mechanical engineers. And it's why it's so important for them to learn early. That's why we at Cal Poly, we go ahead, freshman year, we lockstep you in winter and spring into a manufacturing courses. So you see how manufacturing is performed, and you're not going to be that engineer out there that goes and makes a bad design right away. Well, you might make a bad design here or there, but you're going to have more knowledge on how not to make a bad design before it actually occurs out there. Hopefully, you know that you can't make a 90-degree blind hole if you're going to be machining a part right there and so forth. So that would be an example of one example of design for manufacturability. You've learned a lot about manufacturing in this class, and hopefully you take away some of these design techniques and bring them to you when you go to design your parts for your senior projects, for your junior projects. There's all sorts of cool design projects that you do in your ME degree here. In fact, they make some really cool drill powered trikes I've seen on one of the design projects, and there's some really cool stuff out there. So your lab instructors and I worked really hard to deliver this course for you. And there's an online survey for your lecture and labs basically specific. So you only have a lab section. So it's lab section specific. So if you could take some time this week to go fill that course survey out for your instructor, they would greatly appreciate it. So I think I covered pretty much all of the questions on the test. I'm going to spend a second looking through the test to make sure I covered it. So I got that one good. Vossies, yep. Jigs, yep. Let's see here. Sawing, yep. We talked about that. CNC mills and the axes, yep. We talked about that. Op sheets, yep. Chip load, we talked about that. CMMs, we talked about that. Talked about the radial direction on the lathe. We talked about twist drills. We talked about accuracy. We talked about precision. We talked about routings. We talked about test indicators and dial indicators. We talked about feed and speed calculations for mills. We talked about milling and a turning RPM. We talked about depth of cut for a lathe cut. So I would be able to, if I gave you the measured diameter and the cut diameter, I'd be able to tell me the depth of cut for a turning operation. We talked about that. We didn't talk about it before, but now we did. I would go ahead and know. We talked about tolerances on engineering drawings. We talked about milling. We talked about sawing. We talked about broaching. We're good there. We talked about the thread call out. We talked about tap drills. We talked about pitch. We talked about op sheets. We talked about routings. Yep. We talked about conventional milling and climb milling and peripheral milling and face milling. Yep. We talked about vernier caliper measurements, work holding on a lathe. We talked about that. We talked about boring and we talked about reaming. Talked about drilling, center drills. Basically, we talked about calipers. We talked about facing, turning. Let's see here, feed and speed cow, threads, how to produce threads. We talked about that. We talked about that. We talked about machining processes in general. We talked about shear stress. We talked about chips. We talked about knurling, anodizing, powder coating, galvanizing. We talked about all those. We talked about pitch there. We got height gauges. We got holes for broaching. We got the 5 categories of GD&T tolerances. We talked about that. We talked about cutting fluids and then feature control frames. We talked about that. And we talked about the precision. You've got all 50 questions, I promise you. So have a great week, everybody. If you have any questions, you can email me. Let me go ahead and put that on the screen real quick in case you don't want to go to Canvas and go find it. But it's TGEORGEO@calpoly.edu. So if you want to email me, it's now at the top of the screen, but you can email your lab instructor. They'll be able to answer any questions you have. But have a great week, and please do fill out that course survey for your lab instructors. It makes a difference to them because none of them are tenured faculty members. Their job, basically, they fill out a performance review every year, and their job basically relies on your your surveys go into their performance review. So it actually makes a difference on those surveys. So fill them out for all of your classes and spend a couple minutes to do that. Thank you and have a great day. It's been a fun quarter. I look forward to seeing you virtually in 146, where we'll go through the same weekly topics like this or same lab participation presentations. And then you'll end up getting more time to make your Geneva wheel assembly in IME 146, which we're going to end up making a really cool assembly using CNC milling, injection molding, laser cutting, and water jet machining. And it's all going to basically bolt together to be one product in the end. So have a great day. Hopefully you had fun. Bye.